about differential calculus. And we are going to start from the what is known as the first principles. First principles. Now, differential calculus, by definition, is finding the rates of change in a function. The rates of change in a function, meaning that basically what we are going to be finding is the gradient. And from basic principles, we know that the gradient is always given by the change in y divided by change in x. This is what we're going to be using. Now, I have a function here which I've called f of x. And the whole idea is to find the gradient at this particular point here, A. We know that now, since this is a curve, the gradient along the curve is not going to be constant because the tangent lines will change as you move on the curve. Now, but we can start by finding what is known as the average gradient between 2 points on the curve. I have point A and point B there. I'm joining them with a secant. That is the line that joins A and B straight. Now, let us now suppose that I have a point X on the x coordinates, then I go h steps to the right on the x coordinates, giving me x plus h there. Which means then that the difference between these two here is h. Now, going to these values here, they represent the domain of the function. Going to the range, if my domain is x, then the corresponding range that side is f of x. And if my domain is x plus h, the corresponding range on the other side there is f of x plus h. Meaning that now the change in y is going to be the difference between those two, which is f of x, x plus h, minus f of x, and the difference along the x-axis is h, which then means that the average gradient between A and B is equals to our change in y. We are saying it's f x plus h minus f of x, and our change in x is h. Now, the whole emphasis here in differential calculus is to find the gradient at this particular point here. The gradient at this point here is actually the gradient of the tangent line, that tangent line there. And to find the gradient at this point, which is the gradient of that tangent, it means that we can start from the secant and keep on reducing the value of h such that h goes to 0. That process is known as the limiting process, and it actually gives you the gradient at this particular point here, a. And the notation for that, for the gradient at a, is f dash x. This is the derivative function. It's known as the derivative. F dash x, that's the derivative, which in some cases it's called dy by dx or dx. We'll get to that as we continue with our lessons now. But here we are interested in using the limiting process, which means we have to apply the limiting process. Limit as h approaches 0 of this function here, which is the average gradient, f x plus h minus f of x over h. This is the formula for the limiting process of calculating or finding the derivative of a function. Now, I want us to illustrate this through the examples that I requested you to do, which, okay, question 1 had the function f of x is equals to 2x squared minus x, and you were to determine the derivative f dash x from the first principles. And we know that f dash x, it's given by the limit as h goes to 0 of the function f x plus h minus f of x over h. Then in functions, fx plus h basically means that you are using x plus h as the domain in function f, which means that wherever I see x, I'm going to replace it with x plus h. So that this becomes 2, then there's an x there, which I am going to replace by x plus h, then squared, it's been squared, minus another x there, which I replaced by x plus h, then minus f of x. Our f of x is still 2x squared minus x. Take note that I'm using the brackets here more so that I have a negative sign, which should remind me to change the signs when we expand. And this is the numerator, the denominator is h. It's h. Now, taking it from here, that's the limit as h approaches 0. Then what we're going to do here is just to apply the normal algebraic manipulations. It's 2 times then x plus h all squared. You're going to square x, that's the first term, plus double the product of x and h, which is 2xh. Then the last term becomes the last term squared, h squared. Then I have a minus before the bracket there, which is going to give you minus x minus h. And I also have a minus before that bracket, which is going to give me minus 2x squared. Then negative and negative becomes plus x over h. Now, we are still using the limiting process. Then if we are to expand that, we're going to have 2x squared, I'm expanding there, plus 4xh plus h squared minus x minus h minus 2x squared plus x over h. Then these are inverses of each other and they cancel off. The same applies to negative x and plus x, they cancel off. Which approaches 0. Then I am left with those terms there, 4xh and plus h squared plus h squared. What happened to the 2 here? There is a 2 there, sorry. There is a 2 there from the expansion there. It's 2h squared. So that I am going to be having 2h squared there. Minus h. Yes, minus h divided by h. Then the next thing to do there is we are still applying the limiting process. Factorize, I see an h there, h there, h there. Factorize out h. That leaves me with 4x inside the brackets plus 2h, then minus 1. Yes, over h. Then the h there downstairs cancels the h upstairs. H up cancels the h down, leaving me with the limit as h goes to 0 of 4x plus 2h minus 1, which is the same as the limit as h approaches 0 of 4x plus the limit as h approaches 0 of 2x plus the limit as h approaches 0 of negative 1. Then from the definition of limits, if h goes to 0 and you have a variable there, the limit is going to go to the variable 4x plus this is h, sorry. Now the limit as h goes to 0 of 2h, this is going to be 0, so that the limit here goes to 0, then plus. Now the limit as h goes to 0 of any other variable will give you the same variable, so that this is going to be minus 1, giving you 4x minus 1. Now what we get from here is that if f of x is equals to 2x squared minus x, then the derivative function f dash x or dy by dx is equals to 4x minus 1. 4x minus 1.